We just looked at two examples where we actually calculated the cell potential if we knew what the concentrations were. But a more practical application of how this gets used is to take materials and actually measure the cell voltage and then determine the concentration. So this is a typical sort of a problem. A student wanted to determine the copper ion concentration in a water sample. They set up a galvanic cell connecting 1 molar silver nitrate solution, so it is the silver ion that's going to be doing the chemistry here, with a salt bridge, and they put a copper electrode in the water sample. Putting a copper electrode tells us we're going to have copper solid, and we're trying to determine the copper ion concentration, so that'll be the other half reaction. Then the measured cell potential was 0.62 volts. What was the concentration of the copper? Well, we start off by figuring out what's going on in my beaker. And we have silver ions that can get an electron to make silver solid, and the reduction potential for this is a positive 0.80 volts. The other chemistry is the copper 2 plus gets 2 electrons to make copper solid, and this has a reduction potential of 0.34 volts. That means because silver is larger, this will be the reduction and the copper will be the oxidation half, so that one will turn around. In order to combine these, we need 2 electrons, so we have to multiply the silver equation by 2. And when we do that, we end up with this. 2 silver ions plus copper solid yields 2 silver solid plus copper 2 plus. And looking at this, we can write the Q expression, the ion product, is equal to the concentration of the copper 2 plus ion divided by the concentration of the silver ion squared. Now, we calculate the standard cell potential. Well, E0 for the cell is equal to 0.80 volts, the reduction half, minus 0.34 volts, the oxidation half reaction, is equal to 0.46 volts. So this is my standard cell potential. Now we can go ahead and plug this into the equation. We know that E, the measured potential, is equal to E0 for the cell minus 0.0592 volts divided by N times the log of the copper concentration divided by the concentration of the silver ion squared. Now, this is a little different than those two previous problems because now my unknown is one of the concentrations. So I still just do the same thing. I plug in all my numbers and start to do the math. So my measured cell potential, 0.62 volts, is equal to my standard cell potential, 0.46 volts, minus 0.0592 divided by 2, times the log of Q, which is the copper concentration divided by the silver concentration squared. So we plug this in and we get 0.62 volts minus 0.46 volts divided by a negative 0.0296 volts. I got the 0.0296 by dividing 0.0592 volts by 2 is equal to the log of our unknown copper concentration divided by 1 molar squared. Now it makes it easy because this is 1, because 1 squared is 1. And when we solve all of this, we get negative 5.4. So that means 10 to the negative 5.4 is equal to the copper 2 concentration divided by 1 is equal to the copper concentration. So 10 to the negative 5.4 is equal to the copper concentration, and that is equal to 4 times 10 to the negative 6 molar. So we can use this to actually calculate concentrations, and that's one very common laboratory application of electrolytic cells, is actually calculating how much dissolved metal we have in a sample. Okay, there's one for you to try. Go ahead and do this calculation for that same cell, that 1 molar silver nitrate, but this time the copper ion concentration is 0.57 volts. Go ahead and stop the video while you work the problem. So 0.57 volts, my E that's measured, is equal to the E0, 0.46 volts, minus 0.0592 volts divided by 2 moles of electrons, times the log of my copper concentration divided by my silver concentration, 1 molar squared. So 0.57 volts minus 0.46 volts is equal to negative 0.0296 times the log of the copper concentration. Because we're dividing by 1, the silver cancels. So 0.57 volts minus 0.46 volts divided by negative 0.0296 is equal to the log of the copper concentration, which is equal to negative 3.7. So 10 to the negative 3.7 is equal to the copper 2 concentration, and that is 2 times 10 to the negative 4th molar. So when we look at this, we've done a lot of calculating with galvanic cells, and we think, why are these important to us? It's because galvanic cells in our everyday life make batteries. We know lead storage batteries. These are used in our cars, our car batteries. Zinc, manganese, and nickel cadmium batteries are used for a lot of application. You know nickel cadmium because you hear of NiCad batteries. Silver oxide batteries, these are in cameras commonly. Lithium batteries are in your computers and cell phones. And we also have nickel batteries. So we use batteries in our everyday life, and that's why this is so valuable. The batteries that you buy commercially are lots and lots of little cells stacked on each other, because when we're calculating sometimes the cell potential of one cell, you could see you'd need more than that to make this work. Okay, so that concludes this section, and we'll start the next video with electrochemical cells.